In the vast expanse of the cosmos, where celestial bodies dance through the void with grace and menace alike, there exists a constant reminder of the fragility of life on our planet: asteroids. These ancient remnants of the early solar system, ranging from mere pebbles to monstrous behemoths, hold within them the potential for both wonder and destruction. Among these cosmic wanderers, there is one that stands out, not for its beauty or mystique, but for the sheer threat it poses to life as we know it: Apophis, the most dangerous asteroid known to humanity. As we embark on a journey through the depths of space, our minds filled with awe and trepidation, we must first understand the significance of our quest. The exploration of Apophis is not merely a scientific endeavor, but a vital mission to safeguard our future. In this introduction, we will delve into the history of Apophis, its discovery, and the ominous implications of its trajectory. Through this exploration, we will come to appreciate the urgency of our task and the critical importance of unraveling the mysteries that shroud this enigmatic celestial body. Join us as we venture into the unknown, guided by curiosity, driven by necessity, and fueled by the collective determination of humanity to confront the most perilous threat from the cosmos: Apophis, the harbinger of potential cataclysm. Before we plunge into the depths of our exploration, let us first illuminate the nature of our celestial companions: asteroids. Imagine a vast sea of cosmic debris, scattered remnants left over from the turbulent birth of our solar system over 4.5 billion years ago. Among these remnants, asteroids stand out as some of the most fascinating and diverse inhabitants of our celestial neighborhood. Asteroids, also known as minor planets or planetoids, are rocky objects that orbit the Sun, primarily congregating in the asteroid belt between the orbits of Mars and Jupiter. However, they can also be found scattered throughout the solar system, ranging from the innermost reaches close to the Sun to the outer fringes where the icy realm of the Kuiper belt resides. These enigmatic bodies come in a myriad of shapes and sizes, ranging from small boulders to massive behemoths stretching tens of kilometers in diameter. Some asteroids are little more than rubble piles loosely held together by gravity, while others boast solid cores of metal and rock, remnants of a bygone era when planetary bodies were still forming. Despite their diminutive size compared to planets, asteroids wield immense gravitational influence and play a crucial role in shaping the evolution of our solar system. They serve as cosmic time capsules, preserving precious clues about the early history of our celestial neighborhood and offering insights into the processes that forged the worlds we inhabit today. But for all their beauty and scientific intrigue, asteroids also harbor a darker side. Their orbits can intersect with that of Earth, presenting a constant threat of potential impact. These collisions, while rare on human timescales, have occurred throughout the history of our planet with devastating consequences, reshaping landscapes and altering the course of life itself. As we embark on our journey to explore the most dangerous asteroid of them all, Apophis, let us keep in mind the dual nature of these celestial wanderers, symbols of both wonder and peril, reminders of the delicate balance that sustains life in the cosmos. In the grand tapestry of the cosmos, asteroids occupy a pivotal role, serving as celestial messengers carrying profound implications for our understanding of the universe and our place within it. As we embark on our quest to explore the most dangerous asteroid, Apophis, it is imperative to grasp the significance of studying these enigmatic cosmic wanderers. Understanding solar system formation. Asteroids are relics of the early solar system, preserving within them a treasure trove of information about the processes that shaped our celestial neighborhood over billions of years. By studying their composition, structure, and distribution, scientists can unravel the mysteries of planetary formation and gain insights into the conditions that gave birth to Earth and its neighboring worlds. Insights into Earth's history. Asteroids have played a profound role in shaping the history of our planet, from delivering the building blocks of life in the form of water and organic compounds to triggering cataclysmic events that have reshaped the surface of the Earth. By studying asteroid impacts preserved in the geological record, scientists can reconstruct past events and gain a deeper understanding of Earth's tumultuous history. Planetary defense. Perhaps the most pressing reason for studying asteroids is the potential threat they pose to life on Earth. While the chances of a catastrophic impact are low in any given year, the consequences of such an event could be catastrophic. By identifying and characterizing near-Earth asteroids like Apophis, scientists can assess the risk of future impacts and develop strategies to mitigate this existential threat. Resource exploration. Beyond their potential as harbingers of destruction, asteroids also hold immense promise as sources of valuable resources. From precious metals like gold and platinum to rare elements vital for advanced technology, asteroids are veritable treasure troves waiting to be tapped. By studying their composition and accessibility, scientists can pave the way for future missions aimed at asteroid mining and resource exploitation. Advancing space exploration. Studying asteroids not only enhances our understanding of the solar system, but also lays the groundwork for future exploration missions. Asteroids serve as stepping stones for humanity's journey into the cosmos, offering opportunities for scientific discovery, technological innovation, and the eventual colonization of space. To truly appreciate the significance of modern asteroid research, it's essential to delve into the historical context that laid the foundation for our understanding of these celestial objects. From ancient observations to groundbreaking discoveries in the modern era, the journey of asteroid research is a testament to humanity's enduring curiosity and quest for knowledge. Ancient observations. The study of asteroids can trace its roots back to ancient civilizations, where early astronomers observed the movement of celestial bodies across the night sky. While they lacked the technological tools to discern the true nature of these objects, ancient astronomers recorded the movements of what we now know as asteroids, often mistaking them for stars. Discovery of Ceres. The dawn of the 19th century marked a pivotal moment in the history of asteroid research with the discovery of Ceres, the largest object in the asteroid belt. In 1801, Italian astronomer Giuseppe Piazzi spotted Ceres orbiting between Mars and Jupiter, prompting a flurry of excitement in the astronomical community. Initially classified as a planet, Ceres was later reclassified as an asteroid, sparking interest in the study of these celestial bodies. Formation of the asteroid belt. The discovery of Ceres paved the way for the identification of numerous other asteroids orbiting in the vicinity, leading astronomers to speculate about the origins of these enigmatic objects. It was soon hypothesized that the asteroids were remnants of a failed planet that had shattered into fragments during the early stages of the solar system's formation, giving rise to the asteroid belt. Advancements in observational technology. Throughout the 19th and 20th centuries, advancements in observational technology revolutionized our understanding of asteroids. Telescopes equipped with increasingly powerful optics allowed astronomers to study asteroids in greater detail, revealing their diverse shapes, sizes, and compositions. Radar imaging and space probes further enhanced our ability to explore asteroids up close, providing invaluable insights into their physical characteristics and surface features. Impact hazards and planetary defense. The latter half of the 20th century saw a growing awareness of the potential threat posed by asteroids to life on Earth. High-profile impact events, such as the Tunguska event in 1908 and the Chicxulub impact that led to the extinction of the dinosaurs, highlighted the catastrophic consequences of asteroid collisions. This spurred efforts to identify and track near-Earth asteroids, laying the groundwork for planetary defense initiatives aimed at mitigating the risk of future impacts. Exploration missions. In recent decades, space agencies around the world have launched ambitious missions to study asteroids up close. From NASA's Near Shoemaker mission to rendezvous with asteroid Eros, to Japan's Hayabusa missions to return samples from asteroids Itokawa and Ryugu, these missions have provided unprecedented insights into the origins and evolution of asteroids, paving the way for future exploration endeavors. The early discoveries in the realm of asteroid research represent pivotal moments in humanity's quest to unravel the mysteries of the cosmos. From the serendipitous observations of ancient astronomers to the systematic searches of modern-day telescopes, these discoveries have reshaped our understanding of the solar system and our place within it. The dawn of asteroid exploration. The year was 1801 when Italian astronomer Giuseppe Piazzi made a groundbreaking discovery that would forever alter our perception of the heavens. While surveying the night sky from his observatory in Sicily, Piazzi stumbled upon a faint point of light moving against the backdrop of stars. Initially mistaken for a star or comet, further observations revealed the true nature of this celestial wanderer. Ceres, the first asteroid ever discovered. With a diameter of approximately 940 kilometers, Ceres holds the distinction of being the largest object in the asteroid belt between Mars and Jupiter, marking the beginning of a new era in asteroid exploration. Pallas, Juno, and Vesta, expanding the asteroid catalogue. Hot on the heels of Ceres' discovery, astronomers turned their attention to the space between Mars and Jupiter in search of additional celestial bodies. In rapid succession, 3 more asteroids were identified: Pallas, Juno, and Vesta. These newfound objects, though significantly smaller than Ceres, added further fuel to the burgeoning field of asteroid research, prompting astronomers to speculate about the nature and origins of these enigmatic bodies. With each new discovery, the asteroid belt revealed itself as a dynamic and diverse region teeming with celestial activity, offering tantalizing clues about the early history of the solar system. Asteroid families and taxonomy. As astronomers continued to survey the asteroid belt, they noticed patterns emerging among its inhabitants. Certain groups of asteroids exhibited similar orbital characteristics and spectral signatures, suggesting a common origin. These clusters, known as asteroid families, provided valuable insights into the processes that shape the asteroid belt and the dynamics of celestial collisions. Furthermore, astronomers developed a taxonomy to classify asteroids based on their spectral properties, dividing them into different categories, such as C-type, carbonaceous, S-type, silicaceous, and M-type, metallic. This classification scheme not only facilitated the categorization of individual asteroids, but also shed light on their composition and evolutionary history. Early exploration attempts. Despite their distant and elusive nature, astronomers were eager to learn more about asteroids through direct observation. In the latter half of the 19th century, several attempts were made to study asteroids up close using ground-based telescopes and pioneering photographic techniques. While these early efforts yielded valuable data, they were limited by technological constraints and the inherent challenges of observing faint and fast-moving objects against the backdrop of space. Nevertheless, they laid the groundwork for future exploration missions aimed at unraveling the mysteries of asteroids and unlocking the secrets of the solar system's formation. The quest to detect and track asteroids has been propelled forward by remarkable advancements in technology, revolutionizing our ability to survey the skies and identify potential celestial hazards. From humble ground-based telescopes to sophisticated space-based observatories, these technological innovations have reshaped the landscape of asteroid detection and opened new frontiers in our understanding of the solar system. Ground-based observatories. In the early days of asteroid detection, astronomers relied primarily on ground-based observatories equipped with optical telescopes to scan the night sky for signs of celestial wanderers. These observatories played a crucial role in cataloging known asteroids and tracking their orbits, laying the foundation for future discoveries. However, their effectiveness was limited by factors such as atmospheric turbulence, light pollution, and the Earth's rotation, which could hinder observations and obscure faint objects. Photographic plates and digitization. One of the key breakthroughs in asteroid detection came with the advent of photographic plates in the late 19th century. Astronomers began using glass plates coated with light-sensitive emulsions to capture images of the night sky, allowing for more precise and systematic surveys of celestial objects. With the dawn of the digital age, these photographic plates were gradually replaced by electronic detectors capable of capturing images in digital format. This transition not only improved the efficiency of asteroid surveys, but also facilitated the automation of data analysis and processing, enabling astronomers to sift through vast amounts of sky data more quickly and accurately. Automated surveys and sky surveys. The development of automated survey programs and sky surveys marked a significant leap forward in asteroid detection capabilities. By employing advanced imaging techniques and computer algorithms, these surveys scanned large swaths of the sky with unprecedented speed and precision, identifying faint and fast-moving objects that might have eluded detection in the past. Projects such as the Palomar Sky Survey, the Sloan Digital Sky Survey, and the Pan-STARRS Telescope Array have played instrumental roles in mapping the celestial landscape and cataloging thousands of asteroids with remarkable efficiency. Space-based observatories. While ground-based observatories have been instrumental in asteroid detection, their capabilities are inherently limited by factors such as atmospheric distortion and light pollution. To overcome these challenges, astronomers have turned to space-based observatories equipped with cutting-edge instrumentation capable of observing the cosmos with unparalleled clarity and precision. Space telescopes such as NASA's NEOWISE and the European Space Agency's Gaia mission have conducted comprehensive surveys of the sky, providing invaluable data on asteroids' positions, orbits, and physical characteristics. Radar imaging and characterization. In addition to optical observations, astronomers have also employed radar imaging techniques to study asteroids in greater detail. By bouncing radio waves off the surfaces of asteroids and analyzing the reflected signals, scientists can create detailed maps of asteroid topography and probe beneath the surface to uncover hidden features. Radar observations have provided critical insights into the composition, structure, and rotational dynamics of asteroids, enhancing our understanding of these enigmatic celestial bodies. The identification of potentially hazardous asteroids, PHAs, holds profound significance for humanity's future, serving as a crucial component of our efforts to safeguard life on Earth and advance our understanding of the cosmos. By recognizing and characterizing these celestial threats, we gain valuable insights into the dynamics of the solar system and empower ourselves to mitigate the risks posed by potential impacts. Here are several key reasons why the identification of PHAs is of paramount importance. Planetary defense. Perhaps the most immediate and pressing reason for identifying PHAs is the need to protect our planet from the threat of asteroid impacts. While the likelihood of a catastrophic collision occurring in any given year is low, the consequences of such an event could be devastating, potentially leading to widespread destruction, loss of life, and ecological upheaval. By identifying PHAs and tracking their orbits, astronomers can assess the risk of future impacts and develop strategies to mitigate this existential threat, ranging from deflection missions to impact avoidance measures. Risk assessment and mitigation. Identifying PHAs allows us to conduct comprehensive risk assessments and prioritize resources for asteroid mitigation efforts. By analyzing factors such as the size, trajectory, and composition of PHAs, scientists can estimate the potential consequences of a collision and develop tailored strategies to minimize the impact. This may involve deploying spacecraft to study PHAs up close, developing deflection techniques to alter their trajectories, or implementing early warning systems to alert authorities and the public of impending threats. Scientific exploration and research. PHAs provide unique opportunities for scientific exploration and research, offering insights into the origins, evolution, and dynamics of the solar system. By studying the composition, structure, and orbital characteristics of PHAs, astronomers can unravel the mysteries of planetary formation, cosmic collisions, and the interplay between celestial bodies. Furthermore, missions to study PHAs up close, such as NASA's OSIRIS-REx and Japan's Hayabusa 2, can yield valuable data and samples that shed light on the origins of life and the potential for resource utilization in space. Space resource utilization. Some PHAs may harbor valuable resources such as water, metals, and organic compounds, making them potential targets for future space resource utilization efforts. By identifying and characterizing PHAs with resource potential, scientists can lay the groundwork for future missions aimed at extracting and utilizing these resources to support human exploration and settlement of space. This could pave the way for sustainable space industries and enable the development of a space-based economy. Public awareness and education. The identification of PHAs raises public awareness about the dynamic and often unpredictable nature of the cosmos, fostering a greater appreciation for the importance of planetary defense and space exploration. By engaging the public in discussions about asteroid impacts and mitigation strategies, we can inspire curiosity, promote scientific literacy, and empower individuals to take an active role in shaping our collective future. The discovery of Apophis, often dubbed as one of the most dangerous asteroids known to humanity, stands as a pivotal moment in asteroid research and planetary defense efforts. Named after the ancient Egyptian god of chaos and destruction, Apophis captured the attention of astronomers and the public alike when its potential to impact Earth was first identified. The story of Apophis begins on June 19, 2004, when astronomers Roy A. Tucker, David J. Tholen, and Fabrizio Bernardi were conducting routine observations at the Kitt Peak National Observatory in Arizona. As they analyzed images captured by the Near-Earth Asteroid Tracking (NEAT) program, they noticed a faint object streaking across the sky. Further analysis revealed that this object was a previously unknown asteroid, designated 2004 MN4. What set 2004 MN4 apart from other newly discovered asteroids was its unusually close approach to Earth. Initial calculations indicated that on April 13, 2029, this asteroid would pass within a mere 32,000 kilometers, 20,000 miles, of our planet's surface, closer than the orbits of many satellites. This proximity raised concerns among astronomers about the potential for a future impact, prompting further scrutiny of the asteroid's trajectory and orbit. As additional observations poured in from observatories around the world, astronomers refined their estimates of 2004 MN4's orbit and assessed the likelihood of an impact with Earth. While the probability of a collision in 2029 was eventually ruled out, attention turned to a subsequent close approach in 2036, where the asteroid's trajectory could intersect with Earth's path once again. In December 2004, during a meeting of the American Astronomical Society's Division for Planetary Sciences, NASA scientists announced that the asteroid had been officially named Apophis, after the Egyptian deity associated with chaos and destruction. This choice of name reflected the asteroid's potential to wreak havoc if it were to collide with Earth, underscoring the urgency of further study and monitoring. Over the years, subsequent observations and refined calculations have further reduced the risk of a future impact by Apophis. While the asteroid will make a close approach to Earth in 2029, passing within a distance of approximately 31,000 kilometers, 19,000 miles, the chances of a collision are now considered extremely remote. However, Apophis continues to be closely monitored by astronomers as part of ongoing efforts to track and characterize near-Earth asteroids and ensure the safety of our planet. The discovery of Apophis serves as a stark reminder of the potential threats posed by asteroids and the importance of planetary defense efforts. By identifying and tracking potentially hazardous asteroids like Apophis, astronomers can assess the risks they pose and develop strategies to mitigate the impact of future cosmic collisions. In doing so, they help safeguard the future of life on Earth and advance our understanding of the dynamic and often unpredictable nature of the cosmos. The identification process of potentially hazardous asteroids, PHAs, is a multi-step endeavor that involves the collaboration of astronomers, observatories, and space agencies around the world. This process relies on a combination of observational data, computational modeling, and risk assessment techniques to identify and track asteroids that may pose a threat to Earth. Here's an overview of the key steps involved in the identification process. Observational surveys. The first step in identifying PHAs is conducting systematic surveys of the night sky to search for asteroids. Ground-based observatories equipped with optical telescopes, as well as space-based telescopes and surveys, scan large areas of the sky to detect faint and fast-moving objects that might represent potential threats. Automated survey programs such as the Catalina Sky Survey and the Pan-STARRS telescope array play a crucial role in conducting these surveys and capturing images of celestial objects. Data analysis and processing. Once observational data is collected, it is processed and analyzed to identify candidate asteroids and track their orbits. Astronomers use specialized software and algorithms to analyze images, measure the positions and velocities of detected objects, and predict their future trajectories. This data is then cross-referenced with existing catalogs of known asteroids to identify new discoveries and assess their potential hazard levels. Orbit determination and prediction. After candidate asteroids are identified, astronomers conduct orbit determination calculations to precisely determine their orbits and predict their future paths through space. This involves fitting observational data to mathematical models of orbital motion, taking into account factors such as gravitational interactions with other celestial bodies, the Yarkovsky effect, which causes asteroids to drift due to the heating and cooling of their surfaces, and non-gravitational forces. By accurately predicting an asteroid's trajectory, astronomers can assess its likelihood of intersecting with Earth's orbit and estimate the risk of a potential impact. Risk assessment and classification. Once the orbit of a candidate PHA is determined, astronomers assess its potential hazard level based on various factors, including its size, speed, and proximity to Earth. Asteroids are classified according to their impact probability and energy yield, with PHAs typically defined as those that have the potential to cause significant damage if they were to collide with Earth. The Torino and Palermo scales are commonly used to quantify the impact risk posed by PHAs and prioritize further observations and research. Follow-up observations and monitoring. To refine orbit calculations and reduce uncertainties, follow-up observations of PHAs are conducted using ground-based telescopes and, in some cases, space-based observatories. These observations help astronomers track the motion of PHAs over time, refine their orbital parameters, and assess any changes in their trajectories due to gravitational interactions or other factors. Continuous monitoring of PHAs allows astronomers to update risk assessments and provide timely warnings if a potential impact threat is identified. The initial observations and data collection process in identifying potentially hazardous asteroids, PHAs, is a critical first step in understanding the characteristics and trajectories of these celestial objects. This phase involves systematically surveying the night sky, capturing images of faint and fast-moving objects, and gathering observational data that will later be used to determine an asteroid's orbit and assess its potential hazard level. Here's an overview of the key aspects of this initial phase. Observational surveys. Ground-based observatories, equipped with optical telescopes and advanced imaging technologies, conduct systematic surveys of the night sky to search for asteroids. These surveys typically involve scanning large areas of the sky using wide-field telescopes and sensitive detectors, capturing images of celestial objects that appear as faint points of light against the backdrop of stars. Automated survey programs, such as the Catalina Sky Survey and the Pan-STARRS Telescope Array, play a crucial role in conducting these surveys and detecting new asteroids. Image capture and processing. As observations are made, images of the night sky are captured using electronic detectors such as charge-coupled devices, CCDs, or complementary metal oxide semiconductor, CMOS sensors, which convert incoming light into digital signals. These images are then processed and analyzed using specialized software to identify candidate asteroids and extract relevant data such as their positions, brightness, and motion relative to the background stars. Astrometric measurements. One of the primary goals of initial observations is to accurately measure the positions and trajectories of detected asteroids. Astronomers use a process called astrometry to determine the precise coordinates of asteroids in the sky and track their motion over time. This involves comparing the positions of asteroids in multiple images taken at different times and calculating their apparent motion relative to the fixed stars. Astrometric measurements provide valuable data that are used to determine an asteroid's orbit and predict its future path through space. Photometric analysis. In addition to astrometric measurements, astronomers also conduct photometric analysis of observed asteroids to determine their brightness and variability. By measuring the amount of light emitted or reflected by an asteroid at different wavelengths, scientists can infer its surface properties, composition, and physical characteristics. Photometric data provide insights into the nature of observed asteroids and help classify them into different taxonomic groups based on their spectral signatures. Data sharing and collaboration. Observational data collected by various observatories and survey programs are shared and collated through international databases and clearinghouses, such as the Minor Planet Center, MPC, and the International Astronomical Union, IAU. These organizations facilitate collaboration among astronomers and provide access to a wealth of observational data, enabling comprehensive studies of asteroids and their orbits. By sharing data and coordinating efforts, astronomers can maximize the effectiveness of asteroid detection and tracking efforts and ensure the timely identification of potentially hazardous objects. The classification of an asteroid as a potentially hazardous asteroid, PHA, involves a rigorous assessment of its orbital characteristics, size, and potential to pose a threat to Earth through a collision. This classification is based on a combination of observational data, computational modeling, and risk assessment techniques, and follows established criteria defined by international organizations such as the International Astronomical Union, IAU, and the Minor Planet Center, MPC. Here's an overview of the key criteria used to classify an asteroid as a PHA. Orbital parameters. The primary criterion for classifying an asteroid as a PHA is its orbital parameters, particularly its close approach distance to Earth and its potential to intersect with Earth's orbit. Asteroids that come within a certain distance of Earth, typically defined as less than 0.05 astronomical units or about 7.5 million kilometers, and have the potential to impact Earth in the future, are considered PHAs. The orbits of these asteroids are carefully tracked and monitored to assess their potential impact risk over time. Absolute magnitude. Another important factor in classifying an asteroid as a PHA is its absolute magnitude, which is a measure of its intrinsic brightness. Absolute magnitude is related to an asteroid's size and reflects the amount of sunlight it reflects or emits. PHAs are typically characterized by relatively large absolute magnitudes, that is, fainter apparent brightness, compared to smaller asteroids, indicating their potential to cause significant damage if they were to collide with Earth. Size and mass. While absolute magnitude provides a rough estimate of an asteroid's size, more precise measurements of its diameter or mass may also be taken into account in classifying it as a PHA. Larger asteroids are generally considered to pose a greater threat due to their potential for causing more significant impacts and damage upon collision. However, even smaller asteroids can be classified as PHAs if they have orbits that bring them into close proximity to Earth and pose a non-negligible impact risk. Impact probability and severity. Ultimately, the classification of an asteroid as a PHA depends on its calculated impact probability and the potential severity of the consequences if it were to collide with Earth. This involves conducting risk assessments and probabilistic modeling to estimate the likelihood of a future impact and the potential consequences in terms of damage, casualties, and environmental effects. PHAs are typically assigned a numerical rating on impact risk scales such as the Torino scale or the Palermo scale, which quantify the level of risk posed by a particular asteroid based on its orbit and size. By considering these factors and conducting thorough analyses of observational data and computational models, astronomers can classify asteroids as potentially hazardous and prioritize further monitoring and study of these objects to mitigate the risks they pose to Earth. This classification enables planetary defense efforts aimed at identifying, tracking, and, if necessary, deflecting or mitigating the impact of PHAs to protect life and property on our planet.